Welcome to the Bethe-Kolloquium of November. After the more mathematical theme which we had in October, we this time have a subject which is at the interface of astrophysics, cosmology, and particle physics, much in the sense of Hans Bethe, who has actually been a pioneer in that field. So the subject today is the question of dark matter, which has been discussed a lot in the last decades, and as I see, it seems to raise some interest among the people. We are happy that for this occasion we could convince two renowned scientists to talk about the subject, share their view, the subject. This is Pavel Kroupa from the Argelander Institute of Astronomy here in Bonn, and Simon White from the Max Planck Institute in Garching. We thought that at the eve of the LHC, while there are ongoing direct dark matter searches, and while there are a lot of astrophysical and cosmological observations, we might actually look at this question of dark matter and see what is the status. And so we got two speakers which do not share the same view. They have opposing view, which of course is good for a debate. So, well, since we have a tight schedule, I will not talk too much. And since we started a bit earlier, we might even then start in time with the after having extended the academic quota. So I won't say too much about the two people. Everybody essentially in this one knows them. Nowadays you can see it on the web, just a few short things. They seem to share one thing which I did not know before. They both got their PhD in Cambridge, England. And Pavel Kroupa, he is actually from Australia. He got his degree in England. Then he went to Heidelberg, Kiel, and since 2004, he is professor in the Argelander Institute here auf dem Hügel, as we say. Simon White, after got his PhD, has been at various places, including Toronto, Berkeley, Santa Barbara, Arizona, Durham. And he is now in Munich at the Max Planck Institute and the LMU since 1994, I guess. So that's enough about the people. They will have enough time to tell what their idea is about dark matter. The schedule will be the following. First, Simon White will talk for 25 minutes, and then there will be a possibility to ask a few questions of clarification. Not yet a debate, just urgent question which you cannot keep back, although you should try to do so. After that, Pavel Kroupa will talk for 25 minutes as well. Same rule that there are some questions. After that, I guess each of the two speakers should have 5 minutes again to summarize their main points and also to react on the talk of the previous talk. And then it will be followed by a debate among the two of them. And if we still have time, there might also be questions from the audience. Good, so that's all I want to say. So we start with Simon White, please.
Well, it's a pleasure to be here. So today we're supposed to discuss the interpretation or the existence of a series of phenomena in astrophysics, which have come to be known as the dark matter issue or the dark matter problem. We're supposed to debate this. So I think I'd better start with a definition of dark matter, which I hope at least Pavel can agree to this as just as a definition. So dark matter is supposed to be, I should probably insert here, is supposed to be the dominant material constituent by mass of all objects significantly larger than individual galaxies, but it's so far only been inferred from its gravitational effects. So I hope we could agree on that, with what we're talking about. So the fact that it's only been seen from its gravitational effects then leads to a fundamental question. Does it exist as a kind of matter, or is our theory of gravity incorrect? And so the problem is that the way we've used gravitational forces to infer the amount of matter is incorrect because we've used the incorrect theory of gravity. Now, if it does exist, which is the majority view at the moment, but this is only a view, because as I say, it's only been seen gravitationally. If it does exist, then the next question, of course, will be what would it be made of? And one of the reasons many people feel uncomfortable with dark matter is that it cannot be made of any of the kinds of matter that we already know about and have shown by other means. And so the dominant hypothesis is that it's some new kind of elementary particle which is different from any of the particles that have been seen on Earth. So this is basically the overall issue. So dark matter isn't a new issue in particle physics. It's been around for a long time. Maybe the first kind of dark matter was the inference was the neutron, because this was inferred by Bartziman and Ivenko to be needed in atomic nuclei in 1930. They needed a particle which had no electromagnetic interactions, but still had strong interactions. And of course, its existence was verified by a number of experiments by Chadwick within 2 years. Now, the next kind of dark matter was the neutrino, which was actually, the need was identified by Pauli in the same year, and this was from weak interactions. And there was the need for a particle which didn't interact either by electromagnetically, so with light, or through strong interactions, but through weak interactions. And that was a harder problem. It took until 1956 before the existence of the neutrino was independently verified by other means using the huge flux of neutrinos that you get from atomic reactors. Now, dark matter, the need, was identified by Zwicky at about the same time. And here, it was already in a particle which apparently did not emit light, and since then we've discovered could not interact electromagnetically or with strong interactions, but may not even interact with weak interactions, because it's only inferred through gravity. So there's a kind of hierarchy here. So it took 50 years, actually, until the early 1980s, before all the known particles could be excluded as a possible source for dark matter. The last one were the known neutrinos. The known neutrinos could be ruled out about 1980 because they produced the wrong kind of structure. So there, we still haven't verified the existence by any other means. So we don't know when this is going to happen, if it happens, but it's clearly after 2010. Now, inferring the existence of objects from their gravity is not new. Neptune was predicted by Leverrier and Adams in 1846 from the perturbations in the orbit of Uranus, and it was verified the same year by Galen. Leverrier was very happy with this, so he then moved on to Mercury and predicted an existence of a planet called Vulcan, which was supposed to explain the deviations of Mercury's orbit from Newtonian theory. He was wrong. This was explained by Einstein in 1915 by changing the theory of gravity. Okay, so this is an example of how the other side could be the case. Now, there are other examples, well known, where objects are inferred by their gravity. So I listed two here. All the extrasolar planets, this is one of the great success stories of the last years. We now know about 500 planets around stars other than our own. But 400 of those, their existence is only inferred by the gravitational perturbations on the parent stars. But we don't think that's a new theory of gravity. The other case is massive black holes at the centers of galaxies, in particular at the center of the Milky Way. That's detected only through the motion of the surrounding stars. And so here's the obligatory video from Munich showing the motions, observed motions of stars near the center of our Milky Way. So this image is only 10 light days across. And what you see here are the actual measured motions, and you can see the stars appear to be orbiting around something at the center, which has been, in the image, has been emitted as a white blob here, but it's not seen at all in the real world. And assuming these are Kepler orbits, you infer that there's an object at the center with a mass of 4 million solar masses. So there are plenty of cases where gravity has been used to infer objects, and some where we don't question this, even though in this last case it involves a black hole with 4 million solar masses. So the need for dark matter was inferred first by this fellow, Fritz Zwicky. This was a picture in the 1970s. So he inferred it by measuring the velocities of a small number of galaxies in this particular cluster of galaxies, the Coma cluster, which is the nearest very rich cluster. And what he realized, the relative velocities of these galaxies, there are about 1,000 galaxies in a small region of space, the motions of the galaxies through this region were so large that if they're gravitationally induced, then it needs much more material than he could see in the stars. And so he inferred then there must be a lot of stuff in the cluster which is not visible. That result was correct. I mean, it hasn't changed with much more data. But no one knew how to interpret it, so it's basically sat there for 40 years. An interest in the problem came up again then in the 1970s, when people started looking at objects like this one. This is a galaxy quite close to our own, the Triangulum Nebula. It's a galaxy which is an almost pure disk galaxy. So everything you see here, the stars and the gas, are essentially rotating in a disk about the center. So it's kind of like a mini solar system, but without a sun at the middle, at least nothing you can see. So if you measure the motions of the material about the center, you can plot the velocity of which material moves about the center as a function of distance, and you get a curve like the yellow dots here. That's called the rotation curve. What you can see is the curve rises from the center, and then instead of flattening off or even going down, like it does in the solar system because of Kepler's laws, it actually, in this case, keeps on rising. So if you then use Newton's laws to infer the amount of material here, you infer the further out you go, the more mass you need. Whereas the light, as you can see, stops. And so this led Vera Rubin, shown here in the 1960s, who did this on a number of galaxies, to stress that apparently there was much more mass surrounding galaxies than you could see in their stars from these rotation curves. So this, I think, is today the most direct evidence for the existence of dark matter. So this is actually not the universe today. This is an image of the universe when it was only 400,000 years old. This is the map of the microwave background radiation taken by the WMAP satellite. So what you're seeing here is a direct image of the universe when it was only 400,000 years old. And at that time, it was nearly uniform. You don't see it here, but the contrast between the hottest and coldest points on this map at plus or minus 200 microkelvin. So that means the peak to valley variation is only 10 to the minus 4 of the average value. So it's extremely nearly uniform. And what you're seeing here is small fluctuations in the temperature and also the density and pressure in a nearly uniform mixture of gas and photons. So those are sound waves. And we understand the physics of sound waves. They're linear. These are linear sound waves propagating in a non-relativistic, in a gas, in a plasma of non-relativistic matter plus photons. So since we can understand the physics of sound waves, we can learn about three things from this map. We can learn about the geometry of the universe, its content, and the process which caused the fluctuations. So for today's debate, the second is the important one. We learn about what is present at that time. The way you characterize this is by looking at the power spectrum. So this is the amplitude as a function of wavelength of the fluctuations in this gas, and this is the results from 7-year data from WMAP. So this is the wavelength. These are the long waves. These are short waves on the sky. This is the amplitude. These are the data points. And you can see there's a very clear, pattern here. These are on the large scales, the well-defined amplitude. There's a rise to a peak here at about 1 degree, a trough, a second peak here, this wavelength, a third peak, then quite a large drop. Now these are data from ground-based experiments here, but you can see another peak here, and here, not really, it's in the noise. But certainly 1, 2, 3, very well measured. So this then tells us about the material content, what is driving these sound waves. Now this is actually very sensitive to the presence of something which is not interacting with the photon baryon gas. So let me just show you that. So I'm going to show you is what is predicted. So the red curve here is the prediction of the standard model, which has dark matter and a cosmological constant, all the things you either like or hate. So that's the prediction of the standard model. Let me show you how this prediction changes if I keep everything fixed except the amount of dark matter. So what happens, because I keep the geometry fixed, as the dark matter goes down, it's compensated by the cosmological constant in this case, but everything else is kept fixed. So that means that here, this is the overall amplitude that stays fixed. But look at the difference in the heights of the peaks, and in particular the relative heights of the peaks. This is not a small effect. This is going by 10% jumps from the full amount of dark matter in the first one, which is the model, standard model, to no dark matter, which is the last one. So this is not a subtle effect. It's huge. So if we look at then what they say, this is the parameters measured by fitting this to the standard model. This is the fraction of the energy density in the universe in the dark matter. 23% plus or minus 1.5%. This is a 30 sigma measurement. Actually, more than 30 sigma. Okay. Notice also, this is the measurement of the baryon density, 4.5%, also a 30 sigma measurement. So what you learn from this is the sound waves that we see, the material which is actually interacting with the photons is the baryons, it's this amount, but these waves are being driven by something else, which has to be clumped, it's driving the oscillations, and which is much larger. Interestingly now, the data have got so good, they can put additional limits on other things. So this is a particularly interesting one for a second table in the same paper. This is the total upper limit on the total mass in neutrinos. Now, it's 0.6 eV squared. Actually, if you turn this into an upper limit on the density neutrinos, it turns out they have to be substantially less than the density of baryons. So at least within the standard gravity model, now the data require the total mass in neutrinos to be not more than about a quarter or a half of the mass in baryons. So conclusion from this, at an age of 400,000 years, the mass energy content of the universe was dominated by a non-relativistic, non-uniform component, which had only very weak or gravitational interactions with the baryon photon fluid. And this component could not consist of neutrinos or any other known elementary particle. So then, according to the standard picture, most of our universe today is the dark energy, which we're not talking about here. Roughly 22% is the dark matter. 4% are the atoms, the stuff we actually know about. So this gives us, in the standard model, very well specified initial conditions. So you then ask, how do they grow? This video shows that you start, this is now a calculation of the nonlinear evolution from these initial conditions, assuming Einsteinian gravity. And so what you see is the contrast. This is the expansion of the universe is taken out, gradually grows. The material streams out of low-density regions into high-density regions, streams along these filamentary structures, and makes objects. So this is the nonlinear prediction of evolution from these linear initial conditions, assuming Einstein gravity. So this, you can see, then makes very detailed predictions for what the universe should look like today. And that was the video I showed at the beginning. This is just a fly-through of a virtual universe showing you the range of dark matter structures that are predicted in the present universe by the standard theory. You can see it's no longer smooth at all. There is an enormous range of structures from relatively small lumps like this, which might host the Milky Way, to big lumps like this one we're homing into, which would host a galaxy cluster like the one that Zwicky looked at, according to the standard picture. Okay, so this then is the prediction. So we not only have a very detailed fit to the initial conditions, which requires the dark matter, but in the standard model, we can predict in considerable detail what the dark matter distribution should look like today. So the question then is this supported? So the first thing you saw there is that as objects grow, the material has to stream out of the low-density regions into the high-density regions. So these motions can be detected. So this is another quite precise measurement of this. Now at a redshifts between 2 and 4. So this is when the universe is between about 1.5 billion years old and 3 billion years old. And what's shown here is structure in the gas, the diffuse gas between galaxies, which is observed through the absorption it causes in the light of background quasars. And so then this is a characteristic, this is a wave number, so this is a characteristic size, small wavelengths, long wavelengths. The data here are the data points at different redshifts from about 3,000 quasars. The curves are not joining the data points. These are actually a model based on the standard lambda CDM for what is expected. And the reason the bumps are here is because this actually depends on the actual redshifts of the quasars that we used. And so you can see there's a very detailed agreement. So this means that at redshifts between 4 and 2, the density and velocity perturbations in the diffuse pre-galactic gas are a very close match to those predicted for dark matter-driven quasi-linear growth from the structure we see directly at a redshift of 1,000. So this is a consistency check. We can do this at redshift 0. This is the distribution of galaxies in the nearby universe on the whole sky from this survey. Now, in linear theory, the velocity, our velocity relative to the overall expanding universe, is given by the gravitational force we feel times the time available, with a constant coefficient here that's very close to 1. So you can actually measure this peculiar velocity, because we see this as our motion relative to the microwave background. And this is measured very accurately. It's about 600 kilometers a second. We can estimate the gravitational force by looking at the distribution of galaxies. So we can see the gravitational force only comes from the inhomogeneity. If the universe was smooth, there would be no net gravitational force. Because it's not smooth, there's a gravitational force, and we can observe the lack of smoothness in the galaxy distribution. But then we have to relate the galaxy distribution to the amount of mass. So the assumption, the parameter you actually measure, if you compare the galaxy distribution to this number, is this one, which involves the mass density of the universe, which is dominated by the dark matter, and the amplitude of the fluctuations in the dark matter to the fluctuations in the galaxies. It's what's called the bias parameter. So this is the parameter that's actually measured from this comparison, and this is the value you get from these data and this number. Now, each of these parameters, both omega and this bias for these kinds of galaxies, are measured directly in the standard model. So you can ask, what should you have got? This is the answer, within 1 sigma. So the conclusion then is in the present day motion of the Milky Way is linked to the large-scale distribution of nearby galaxies, just as expected for linear growth according to standard gravity from a universe which started with the properties you see in the microwave background. And you can do the same test for the detailed velocity field on large scales in the local universe, and you get essentially the same result. This is a picture of the predicted dark matter distribution from the simulation I just showed you. According to the standard picture, the galaxies we see formed as gas condensed at the center of each of the dark matter lumps. So you can model that in a physically reasonable but approximate way and predict what the distribution of light should be. So inside the computer, you now have a prediction of where the brightnesses of all the galaxies in your computer universe would be. So you can send in a virtual telescope, observe the virtual universe, and make a survey of the virtual universe that you compare with surveys of the real universe. And this is what you get. This is a survey of the galaxy distribution in the real universe. We are here. This is distance away from us, and this is one angle on the sky. And this is a redshift survey. This is a survey of the virtual universe made in exactly the same way. These are surveys of the real universe at a different scale. That's why the structures look bigger here than here. These are surveys of a virtual universe made in the same way. So what the question then is there a good statistical match? And the answer is, by most statistics, the match is actually quite close. So what you learn then is the statistics of the large-scale distribution of galaxies agree in detail with those predicted for growth according to standard gravity from the initial conditions seen in the microwave background, assuming that galaxies form when gas condenses at the center of all these dark matter halos. Right? So if you make these assumptions and work it through, you can get a close fit. Let's come to individual objects. I won't show you the update of Zwicky's test, although with better data, his result still holds. This is a different observational test of rich galaxy clusters. If you look at rich galaxy clusters, they contain a static atmosphere, or nearly static atmosphere of hot gas which emits in the X-rays. And so you can measure its density and its temperature directly with X-ray telescopes. If it's sitting there in equilibrium, then if you know the density and the temperature is a function of position, you can use the hydrostatic equilibrium equation to figure out the potential well. And that gives you a mass measurement. So mass is measured in this way. This is a mass. This is radius, both logarithmic. So there are, I think, 10 clusters here. And then this is a prediction for the standard model. And there's effectively no real free parameter here, because the temperature is adjusted, is measured for the global temperature. That's what you adjust to the model, and then you just put the mass on. Okay, so that's the level of fit that you get. However, you can look in other ways. You can use gravitational lensing. You see these strongly distorted objects, background galaxies being gravitationally lensed by this rich cluster. You can use the gravitational lensing also to measure the masses of clusters. So now this is very complicated, but all you need to know is there are 6 panels here, which are clusters of different inferred masses from 10 to the 13 to 10 to the 15. The data points are the distribution of mass inferred from gravitational lensing, and then the curves are what is inferred by the standard model. And here, the way these are fit, there are essentially no free parameters in this fitting, because we've used the number count of the galaxies to decide which cluster should fit. And you can see, in all cases, it fits quite well. There are small offsets, which maybe we have the wrong parameters for the standard model. So the conclusion then is that mass structure of galaxy clusters inferred by standard gravity agrees in detail with that predicted in a cosmology which fits the microwave background and includes dark matter. And this is true whether you use galaxy motions, hydrostatic equilibrium, or gravitational lensing. And the latter is important because it means that both the photons and non-relativistic particles, like the galaxies or the gas atoms, are affected by the unseen mass, or whatever it is, in the same way as predicted by by general relativity. Here's a famous case. This is a cluster where you can see it has 2 pieces, one of many galaxies here and many galaxies over here. If you infer the mass distribution from gravitational lensing, you find most of the mass appears to be in these 2 places behind the galaxies. When you look with an X-ray telescope, you find most of the observed material is actually here and here in the middle. So it seems that the mass detected by lensing agrees in its distribution with the positions of the galaxy clumps, which in terms of the baryon mass are actually subdominant, and does not agree with the position of the X-ray gas, which is the baryonically dominant component. So that suggests that there must be another more massive component, or something which is sourcing the gravitational lensing, which coincides with the galaxy positions. This is satellite galaxies. Let me skip to this. So we see many galaxies orbiting individual halos. So we can ask, what is the relation, can we make a measurement of the relationship between the mass of a galaxy, this is in solar masses, our Milky Way would be here somewhere. This is the mass of the galaxy and the mass of its dark halo. And this is what you get from 3 different arguments. The circles here inferred by gravitational lensing, just as we saw for the dark matter clusters. This is the relation. This is obtained by stacking lensing results for many galaxies. The triangles are inferred by using the dynamics of the small galaxies orbiting around the big ones, again, averaged over samples of large numbers. And the curve here is what you get just from a counting argument when you count how many lumps there are as a function of mass in my random CDM universe, how many galaxies there are as a function in the real universe, and if you assume there's a one-to-one relation between the mass of the dark matter and the mass of the thing you see at the center, then you can predict how these should be related. That's this curve. You can see all 3 of these ways of inferring the mass of the dark matter around a given halo agree with each other. So the conclusion is the mass structure predicted by the standard cosmology for the dark halos of isolated galaxies agrees as a function of their stellar mass with that inferred directly both from lensing and dynamical data. And this way of looking at the comparison had no free parameters. I'm going to skip this to get to dwarf galaxies since I'm running out of time here. So I think Pavel will probably talk about dwarf galaxies, so let me introduce this. So these are the smallest galaxies around the Milky Way. Their luminosities, the Milky Way in these units has a luminosity of about several times 10 to the 10. So this one is already less than 1,000th the luminosity of the Milky Way. You see we have about 5 orders of magnitude in the brightness, the number of stars in the objects. And this is the mass inferred from their motions within a standard radius. You see the other surprising result, the mass inside this standard radius appears not to depend on the luminosity. So it looks as though the apparent mass of dwarf galaxies is independent of their baryonic content. So it seems as though whatever's causing the motions is dominated by a different component. So it seems, I think we all agreed that dark matter has not yet been seen directly. So its existence is still a hypothesis that we have to test. But I hope I've shown you that there's observational evidence for an unseen source of gravity at times in the universe's history between 380,000 years, which is the microwave background, and today, which is 13.7 billion years, and on scales of 10 to the 7 solar masses, which is the smallest dwarf galaxies, to 10 to the 18 solar masses, which is the scale responsible for the microwave background fluctuations. And I will claim that a new weakly interacting massive particle is currently the only hypothesis which is demonstratively and quantitatively consistent with all these data.
Thank you very much. Are there some questions?
Yeah, just 2 points about your fundamental evidence for dark matter. In the coma cluster, whereas Wiki found it that you mentioned, you would agree that the discrepancy he found was something like, in your terms, a factor of 600. That was the missing mass discrepancy then. It's only a factor of what now, Simon? 4 or 5? And that depends on the Hubble constant. So you would agree that that fundamental bit of evidence has, in some sense, become much less with the discovery of the X-ray gas.
No, I disagree. Because the reason, the current discrepancy between the mass of the coma cluster and the baryon cluster is a factor of 5 or 6 that I agree with. But the reason is that we now see the baryonic component between the galaxies, the X-ray emitting gas. The discrepancy for the galaxies is still nearly a factor of 100. So he got a number which was too big because of the Hubble constant, as you say, but the discrepancy between the mass of the galaxies and the total mass of the cluster is still close to 2 orders of magnitude.
Another point, WMAP, you've got 30 sigma results. Sorry, you have 30 sigma results for parameters. If the errors are statistical accurate like you hope they are, but of course the more people that look at WMAP data, the more issues we find with that data. Some people find that the radio sources are more blurred in that data, the telescope is blurred, and it turns out that would have a huge impact on the interpretation of WMAP results. Other people have for a long time talked about the anomalies at large scales. These two things may be connected.
This is not yet a debate. So if you have some urgent questions, please, because otherwise...
There are no published data which show an error in the WMAP analysis.
That is not true.
Okay, so we can... Here's another question there.
Simon, a little bit more careful. Isn't it critical, for instance, already to accept that the clusters are virialized? Because we know that they merge, they form substructures, and this means all the interpretations of the velocities and velocity dispersion, and also of the temperature, the density, might be misleading.
The detailed simulations that I show you include all these effects because we see the assembly of the cluster, so therefore we have the deviations from virial velocities, we have the internal motions of the gas. So it's true, these shift mass estimates by small amounts, but they don't shift the conclusion at all.
On the table where you showed the results of the WMAP analysis of anisotropes, the results for the parameters of the universe, there were 2 numbers there for the sum of the masses of the neutrinos.
Yes.
What is the difference between those 2?
This depends on whether they assumed a cosmological constant or they allowed a different equation of state for the dark energy. So if you take this one, then the upper limit on the neutrinos is 1/4 of the mass of the baryons. If you take this one, it's just under half the mass of the baryons.
And these are entirely from WMAP data?
These are, no, here they're assuming, they've assumed, basically this is the local density, this is the length scale, so they have assumed a Hubble constant, which Tom would undoubtedly want to quibble with, but this assumes the locally valued, a particular locally estimated value of the expansion rate of the universe today. These are the values just with only the WMAP data. So actually for this particular, it makes a difference for this one, but not much for this one.
Okay, it seems there are no more questions, so thank you very much again. Okay, so you see the opposing view already in the title, and I guess we have now Pavel Kroupa, who will tell us about his point of view.
Okay. So, lambda CDM is ruled out, and I want to start with a historical perspective. 500 years ago, there was an excellent standard model, and that was the geocentric model by Aristoteles. One had to make the theory fit to the data by inventing epicycles on epicycles and moving the center of the universe, which was the Earth, away from the Earth to make it fit. It left an excellent description of the data. How it was complex and a lot of people didn't actually like it so much. An alternative model existed by Aristarchus. That was the heliocentric model. It was not accepted because it was more complex and unsatisfying. There were two centers, and it does not fit the data. There were two centers because one had to have the sun as the center of the universe, around which the planets moved, and the Earth as well, around which the moon moved. So it was more conceived to be more complex and less satisfying. The decision came by technological advance when Galileo's solar system telescope data disproved the standard model. Galileo saw that Jupiter has moons. That means there were at least two centers in the solar system, the geocentric model, and that is the Earth and Jupiter. So the phases of Venus clearly show that Venus had to move around the sun. And so a world beyond the standard model is seen for the first time through the telescope. However, at that time, there was absolutely no idea of what the deep physical meaning of that was, because Newton had not been around at that time yet, nor was Einstein. So the conclusions from this little historical escapade is that it is irrelevant today to debate whether the geocentric model fits any data. Also, beauty or even high precision of a model can misguide. The current worldview is that based on general relativity, that it is valid in a weak field limit. This can be tested by studying the dynamics and structure of galaxies, for example, in the local group and local volume, where we have the best available data here, and also that the matter is conserved, which means that it's produced during the Big Bang and is there since then. So this can be tested by studying the matter cycle. So this leads to a cosmological model in which structure is generated by dark matter into which baryons fall, fueling star formation activity of galaxies, as Simon has very beautifully demonstrated. And of course, this has to be valid in the local group and the local volume. So step one is we have a convincing, beautiful theory. It is the standard concordance cosmological model. Lambda CDM is equal to concordance cosmological model. Simon showed the excellent fits to many data which we have today. Step two is making the theory fit. Einstein-Newtonian gravity can only be made consistent with the data by adding inflation, dark matter, dark energy, dark force. That's a very new phenomenon which is now being discussed by Peebles and Musa, 2010 in Nature Review. So this is the standard concordance cosmological model. This has problems. Inflation is not understood really. The detailed particle physics mechanism is not fully understood. Dark energy has problems because the implied dark energy density is so small that it is unstable to quantum corrections. It is not seen by WMAP. At least there's an issue. Energy creation, which means universe expanding. You get more and more energy out of nothing. It's an energy creating model, and it may not be there at all, according to Wiltshire. Dark matter, despite much search hitherto unknown stuff, and whatever you do, you cannot falsify it, because there's always a particle just below the detection threshold of the newest billion-dollar experiment which you might be building. It is not falsifiable. Baryons, we've only seen a small fraction of what they should be. The rest of it does not seem to be accounted for. And dark force, well, totally unknown. Step three, an alternative exists. The primary arguments for cold or warm dark matter comes from flat rotation curves. So we've already had a discussion of this. We have here many rotation curves. The issue is here that as you go outwards from a galaxy, this is in kiloparsecs from the center, you move up, the rotation curve becomes flat at some distance. For example, this is where the sun is at 8.5 kiloparsecs, and some of these rotation curves go out to 40 kiloparsecs. Now, Bosma, who was publishing this, concluded that perhaps a substantial fraction of the mass is not distributed in the disk at all. That means dark matter is probably in a spheroidal halo. This leads immediately to the problem that there exists an unexplained disk halo conspiracy, because the visible matter of a galaxy is declining exponentially outwards in radius, and the dark matter halo has to pick up just in the right way to give these flat rotation curves in essentially every galaxy. And this is not explained. Flat rotation curves are in fact explained much better by non-Einsteinian turning gravity, for example by MOND or MOG, modified gravity, modified Newtonian dynamics. So given an observed baryonic matter distribution, you observe a galaxy, measure its light, from that alone you can predict precisely the rotation curves, and you cannot predict the rotation curve using lambda CDM. Here's an example, this rotation curve. You see the wiggle. This is in MOND, because in MOND you only use the observed matter distribution to get the rotation curve. In lambda CDM, there's a mismatch here and there's a mismatch here, because you need the dark halo to give you the extra gravity. Plus, in MOND, dark matter significantly reduced in galaxy clusters. One does not need as much dark matter in galaxy clusters if one works in the framework of MOND. So there's a review here on that. Now, there are statements on large-scale structure formation. Simulations yield comparable results between MOND and the standard model for the large-scale structure. We show that it may be possible to reproduce observations of the cosmic microwave background and galaxy distributions with Bekenstein's theory of MOND. And there's a perfect fit to the Cmb peaks with the 11 electron volt sterile neutrino. So this is now the Cmb Power Spectrum, published by Angus, 2009, and you can see it's an excellent description of the data in a MOND framework. And here's a previous work by McGough, which was concentrating on the first two peaks, and it had no dark matter, cold dark matter.
Isn't that dark matter?
Which
11,
one?
11 eV star.
Yes, but it's hot. It's not cold dark matter.
It's still dark matter.
Yes, that's fine. Yeah, that's perfectly okay. So the numerical tools, anyway, so numerical tools are nowhere near ready, okay? Gary Engels writes this. Basically because the 2 or 3 people with the necessary expertise to develop the codes can't get jobs for love of money, which means we simply do not have the knowledge what a universe would look like in an alternative framework as we do in lambda CDM, because essentially nobody can do the work because there's no jobs for that. You can't build a cathedral with no people. So the concordance cosmological model does not uniquely account for the CMB nor large-scale structure. So there are 2 hypotheses, standard and the exotic gravity models, and in a perfect world we would of course be able to investigate both, but there are sociological issues. And here today young researchers are afraid and discouraged to try alternatives. This is unfortunately the case. This is why I'm mentioning this. There are some personal examples which I want to mention. For example, you have written that paper on DSPH satellites without dark matter. You are unhirable. It is not worth reading those papers on satellite galaxies, but everyone knows that MOND is crap. In Baltimore, 2010, this year, I heard it with my own ears. I would be scared, mostly because I'm still in search of a permanent post, of being labeled once and for all as a hardcore Mondian person, as if being labeled a hardcore LCDM person were acceptable. And I can't do any work on MOND. It would not be appreciated in the institute. So this is a no-go. And this is where what you do. That's the party line. That's where the resources are going. You do that to get a job. Now, step 4, decision made possible through technological advance. Assume standard model is correct. There are 2 tricky conjectures of fundamental importance. One, they must be dark matter. Second, tile dwarf galaxies form out of the collision debris of other galaxies. He was one of perhaps the first one to actually put up these conjectures, and both have to be true. So we have here the structure formation tree. Small dark matter halos form first. They accrete baryons, which make stars. The dark matter halos merge to make the current dark matter halos in which the galaxies are a small baryonic object. This is what a dark matter halo looks like. There's a negative image. Our Milky Way would be a small disk like that in here. This is the size of about 500 kiloparsecs. And there are these many substructures which are milling around in this object. So this has 2 immediate implications. There exist large numbers of dark matter-dominated satellite galaxies. There exist large numbers of newly formed tile dwarf satellite galaxies that do not contain dark matter. This is okay, but are there two different types of dwarf galaxies? Because we expect the one case, galaxies to form in dark matter halos, and in another case, galaxies to form without dark matter halos. Those are the tile dwarf galaxies. Here's what we know about stellar systems. Here's the size against luminosity, faint, bright. This is 1 million solar masses. Here are star clusters, and this is where what we call galaxies appear. Up here we have 10 to the 10 to 10 to the 12 solar masses, so these are elliptical galaxies, and these are our objects of interest, the dwarf ellipticals and dwarf spheroidal satellites, and we see there's only one population of galaxy. We do not see a spreading or two populations. So the answer to this is no, there is only one type of dwarf galaxy, but which one? And why only one? Let's first look at the dark matter type satellite galaxy. This can be tested by looking at the mass-luminosity relation, which Simon has already mentioned. So we have here the mass of the dark matter halo, and here the luminosity of the object. What we expect is that the more massive satellites would be brighter. Larger bucket holds more water. That's essentially the physics behind it. And so we expect a positive slope. So there's a log mass versus log luminosity relation, which can be specified by the slope. And this is what the theoretical models show. You can see here there is indeed a slope. The more massive satellites in the theoretical lambda CDM models are brighter, which means that the dark matter models are okay and they are internally consistent. And we've already seen that the observations show a very different picture. This is what we expect, and that's what we see. Reality does not care about the dark matter in these systems. Okay? Thus, the concept of dark matter halos appears to be unphysical for those spheroidal satellites. Dark matter halos, I think, are ruled out. But that's only one argument. We could always say there's an error in the argument. Let's look at morphology. Here, the idea is that we observe that the stars move with 7 kilometers per second in these objects, which means that in a few 100 million years, they cover the size of the object. And so any substructure in the satellite should phase mix away if this velocity dispersion is really due to a dark matter halo. So however, we see significant isotope distortion in many of the dwarf spheroidals. Is this consistent with dark matter? Well, here are some examples. This is Ursa Minor at a distance of 65 kiloparsecs. It has about 500 parsec size. And this S shape and general morphology is simply not really consistent with it being in this 10 to the 9 solar mass dark matter halo. What you have to realize is that this thing is in a dark matter halo which is vastly larger than this satellite. Here's another case, Fornax, at a much larger distance, and you can see how distorted and off-center the isophotes are. And this is, again, not consistent with being embedded, shielded by an extensive dark matter subhalo, unless it was very recently hit by something. And there are many other cases. So the distortions apparent in many of the dwarf spheroidal satellites do not support the notion that they are shielded by these large dark matter halos. So dark matter halos are ruled out. That's another argument. The spatial distribution of Milky Way satellites is another way of looking at the satellite population. Gives us further clues. This is what it should look like. Our Milky Way is a little disk in here, surrounded by all the substructure. The substructure is essentially nearly isotropic around this system. It is not anisotropic. This is what our Milky Way looks like. So we have here the Milky Way disk, and these are satellites. These are the classical bright satellites, and these here are found by robots. A very different discovery history to these satellites, a different type of population, if you like, in terms of how they were discovered. This is going from, so this is the whole virial radius of the Milky Way. And if you turn this by 90 degrees, you see that they are highly anisotropically distributed. So is this a structure which actually is a rotational object? For example, a disk which is rotating like this. Now, what we can do is fit a plane to this and get a normal. The normal is defined by the outer satellites. However, the angular motions of these satellites are given by the inner ones because that's where we can measure the motions. These are too far away to measure the motions. And we find, so this is now the galactic sky, and these are the directions of the orbital angular momenta of these satellites, and they cluster, as you can see, with an uncertainty around here. Now, this is the normal of the bright satellites. and this is the normal of the independently discovered faint satellites. The fact that these are so close together shows that there's a correlated phase space population which is inconsistent with the satellites being dark matter subhalos that fell into the Milky Way halo in a group or individually. You can't get that sort of structure if you assume that they fall in individually. So the dark matter halos, I think, are ruled out. So within about 2 megaparsecs of the local group, we should not actually get the local group because having a local group is extremely unlikely. The argument there is you have 2 massive dark matter halos in the local group, Milky Way Andromeda, similar mass, and the probability that they are occupied by similar Milky Way, similar disk galaxies with similar satellite populations is known today from the lambda CDM simulations to be very unlikely. Okay, so these are just some numbers. And within 8 megaparsecs, that's a local volume. Again, so the likelihood of having the 3 massive galaxies above the local sheet is very small. And there are far too few galaxies in the void. And again, this likelihood of having that in a lambda CDM universe is very small. Furthermore, disk galaxy is far too similar. This is the invariant disk galaxy. You take one disk galaxy, you can actually compute what another one will look like. This is not possible in lambda CDM because the galaxies have very different merging histories. They live in very different environments. The angular momentum in the galaxy should be different. 30 to 60% disk galaxies are bulgeless. There's no evidence for merger built-up bulges in a large fraction of the disk galaxies. Again, this is a very major problem for lambda CDM. So, do we live in a bubble of extreme exception? I think this is not the case. I call this the BEE hypothesis to save the concordance cosmological model hypothesis. And I think that is not the way to go. The dark matter ansatz fails. So let's now look at the alternative. Let's consider now the tile dwarf galaxies, Zwicky's second conjecture. Tile dwarf galaxies form when disk galaxies interact. These are disk galaxies with gas. You can see that as they collide, matter is thrown out, and you can see these objects which form. And these are the tidal dwarf galaxies. They are small dwarf galaxies. This is observed to occur. And here's another image. We have star formation in galaxy-sized clumps between the galaxies. So by direct observation, we see that new dwarf galaxies form, and they are baryon-dominated. We know that they can't capture the dark matter if it is there. So evolution of these tidal dwarf galaxies, are they stable? Do they survive? Take one of these, put them into a computer and evolve their evolution as they orbit for many billion years around a major galaxy. And this is what you get. The remnants, these are 2 snapshots on different orbits. The remnants have highly anisotropic phase-space distribution functions. They have baryonic masses of 10 to the 5 solar masses, few hundred parsec size, and large mass-to-light ratio, although they do not contain dark matter. Let's look at Hercules at 130 kiloparsec. You can see how squashed it is. And you see the size. It's about 180 parsec radius. This is an object which was calculated in 1997, and these parameters are amazingly similar to Hercules, with a large mass-to-light ratio but no dark matter. And this is a real prediction 10 years before the discovery of this type of celestial object. Now today we know that the early star formation and chemical enrichment evolution is similar to the observed dwarf spheroidal satellites of these tidal dwarf galaxies. Today we know that later dynamical evolution does not destroy the satellites. We know today that the number of old tidal dwarf galaxies amounts to the DE population observed. We also know that the DE galaxies are observed to contain no dark matter, consistent with them being tidal dwarf galaxies. Young tidal dwarf galaxies have rotation curves showing the missing mass syndrome, but they cannot have dark matter. This may be a real evidence, real measurements of the breakdown of Newtonian gravity, and might be a real falsification of LAM-CDM, but we only have 3 of such galaxies observed. Clearly, we need more of them. So, what about the disk-like configuration? Remember the anisotropy distribution of the satellite galaxies? And there's a relation between the bulge luminosity and then the satellites. So this is easily understandable. Well, this is actually what we observe. So Andromeda has a more massive bulge than Milky Way, and it has more satellites. And this correlation is stressed first by Karatchentsev et al. Using local volume galaxies. Both the disk of satellites and bulge satellite correlation are easily understandable in this scenario because phase space correlated satellites form naturally in the same event as the bulge does. You don't have to invent any new physics to get this sort of correlation. The mass luminosity non-correlation, well, there's no dark matter, so we don't have to worry about the amount of dark matter in these objects. And tidal dwarf galaxies are known to form. They are the result of well-understood standard physical processes. Thus, a fully self-consistent tidal dwarf galaxy scenario emerges, which very naturally accounts for the properties of these DE galaxies and dwarf spheroidal satellites. There's no consistent, in fact, a contradictory picture within the dark matter framework. There is simply no evidence for the existence of dark matter satellites, unfortunately. I think the theory is very beautiful, but it just has a problem. It doesn't work. Every prediction of the standard cosmological model failed. In fact, some failures can be resolved by introducing unknown physics. But on galaxy scales and beyond, failure remains the rule. There's this disk-halo conspiracy, invariant disk galaxies, preponderance of disk galaxies without bulges, likelihood of having a local group being essentially negligible. And you can make a list where standard model fails. Mond, in this case, Mond, does well, but not always. We don't know because we simply don't have the resources to look at every single possibility. And remember this slide? Well, I think this is the correctest description of the situation. Standard model out, alternative in. So conclusions with some history. We had this slide with the geocentric worldview. It's exactly the same slide, just with a few words changed. The LCDM model based on Einstein. Make it fit by inventing inflation, dark matter, dark force. It's an alternative, more not accepted. It's deemed to be more complex and unsatisfying. More needs dark matter. Does not fit the data well, is claimed. Decision by technological advance. Local group telescope data disprove the standard model, but are consistent with non-Einsteinian Newtonian dynamics. Conclusions: it is irrelevant to debate whether the LCDM model fits any data. The relevant issue now is what are Mond or Mach, etc., telling us about space-time inertial mass. And I think this is actually where one is seeing new physics, which is worthy of exploration. I'm not saying you should stop everything on lambda CDM, but that alternative is very important. And it's a pleasure to introduce these three people, Sanders, Hensel, and Shanks, who've come here on my invitation to be part of the debate, because I can't obviously answer all questions since I'm not fundamentally a cosmologist. So there are expertises here which would be useful. And I want to leave you, I'm finishing now with this new structure formation picture, which is based only on baryonic galaxies, where galaxies collide, and when they collide, which is then not so often, they spawn these new galaxies. So today you see the Milky Way plus its satellite galaxies. And that would be all. Thank you.
Thank you very much. Thank you very much. There's a question there.
For the simulations of the tidal dwarf galaxies, they assume alternative gravity or Newtonian gravity?
That's a very good question. All of that was done in Newtonian dynamics, because we don't actually have a code to do that in an alternative gravity framework. I'd love to do these calculations with a non-Newtonian code, but that code has to first be developed to suit those needs. And working in Mond is numerically much more difficult, because the external, so the boundary conditions are so much more difficult to handle. So we need expert people to develop these codes and then do these simulations. The reason why it works with Newton is, first of all, Newton is pretty good. You know, it's very close to the truth, but it seems that the external field effect might be kicking in here. So in Mond, if you have a substantial external field, it actually suppresses the Mond effect and the objects start looking like Newtonian objects. So this might be a reason why the Newtonian simulations seem to work fairly well. I wouldn't say we get it spot on, but it's pretty good.
There's a question over there.
Could you explain a little bit more how you think Mond might actually match that data?
Well, I'm certainly not the correct person to ask that in detail, but from being in touch with Gary Angus, who has looked at this, who's actually done these calculations, it seems that the Mond effect, non-Newtonian effects or non-Einsteinian effects would not actually be very relevant in the very early universe where you have very high densities. And so you're still nearly in the standard framework, except that you then do need dark matter, as correctly pointed out by Simon White. And the interesting result by Gary Angus actually is, and this is published work, is that in order to fit the current WMAP data, you need to invoke 11 electron-volt stellar neutrinos. And you can then ask the question, is that hypothesis in Mond consistent with, say, galaxy clusters? Because you'd have to, because in Mond, you also need dark matter in galaxy clusters. You need far less, but you still need some. And they've looked at this Tremaine-Gunn phase space limit, and Gary Angus finds that indeed it's beautifully consistent for many galaxy clusters. You get the same result as for the WMAP result. So there's again a consistency argument which doesn't prove the theory or that approach, but it gives a suggestion that there is definitely there's a non-unique solution to the galaxy clusters or large-scale structure essentially and WMAP results. So it's not only lambda CDM, but other approaches would also be working.
Simon?
Yes, I'd like to comment on that particular point, which will come back later, but since it came up now, it's useful. I think, as you showed, Gary's model is a beautiful fit to the WMAP data. That is because it is, in fact, the same model the WMAP people fit. It has the same Hubble constant, the same geometry, the same baryon density, and the same density, 22% of dark matter in a new elementary particle not yet seen on the Earth. So in fact, it is exactly the same model. The only difference is in the identification of what the dark matter particle is. So that is the standard model, except for the nature of the particle. And the reason it evolves to the same thing is because if you start from those initial conditions, it will evolve and produce clusters in exactly the same way. So that model fits, but does not need Mond.
Except if I could, can I?
Yeah.
So because if you are then saying that you have 11 electron-volt stellar neutrinos, then later on you do need Mond to expand the galaxies, right? So in that sense, one does need Mond. And also the galaxy clusters, of course, you require non-Newtonian dynamics.
No, the galaxy clusters are okay. The galaxies, I agree.
Okay, that seems...
You didn't say anything about the bullet cluster, which I thought is usually touted as being very difficult for Mond theories.
That is a wrong statement, actually, because if you are again in this framework with 11 electron-volt stellar neutrinos, which might actually be found in Karlsruhe within some years, possibly, then the bullet cluster is perfectly okay. I mean, whatever you do in Mond, you do need dark matter, and the dark matter would behave just like is evident in the images. So it separates away from the gas, follows the galaxies, and there's no issue. In fact, the problem with the bullet cluster, as stated by those people who've looked at this problem, is that it is inconsistent with lambda CDM. So I don't know if Simon will comment on that, but probably you will. But the problem with the bullet cluster is that this is work by Gary Burkhardt and some other people. You require in lambda CDM a certain velocity of the two. It's about, to get that morphology. That velocity is extremely high. It's about 3,000 kilometers per second. And apparently this velocity is not obtainable, at least not easily obtainable in lambda CDM, right? So it's actually a counter-argument. It actually disproves lambda CDM. However, if you are in a Mondian framework, you get those sort of velocities naturally. So the bullet cluster, in fact, can be interpreted to be a major problem for lambda CDM and a perfect agreement with MOND plus the hot dark matter. And there's another cluster which is called the Trainwreck Cluster, which usually people don't talk about, and that seems to be a major problem for lambda CDM.
Good. It seems that all the urgent questions have been asked, so I guess we close here again. Thank Pavel again.